Hello! Today I'm going to be doing a demonstration on how a Van de Graaff generator works. So a Van de Graaff generator was invented originally in 1929 by Robert, you guessed it, Van de Graaff. Alright, so first off we're going to do a fun demonstration. As you can see, this is a metal sphere, which is a conductor. So that means that electrons can flow freely. Now, if I place my hand directly on the Van de Graaff generator sphere, all of those charges will be able to flow towards me because humans are actually good conductors. Now, also notice that I am standing on a plastic crate, which is an insulator. So that means that charges cannot flow freely. So now we're going to go ahead and start cranking the generator, and let's see what happens. Alright, I think that's good. So the reason why my hair is standing on end is because currently I am charged right now. And like charges repel, and so you can see that my hair is repelling away from each other because of those like charges. And now as soon as I step down off of this insulator, all of those charges will go into the ground and I will discharge.
Next, let's discover the different components of the Van de Graaff generator to better understand how this complex machine works. On the right is the metal conducting sphere, in the middle is the metal neutral wand, and the left is a complex pulley system. The top there is a metal comb, as well as one at the bottom, and also two plastic rollers, one on either end, that are connected by a rubber belt. Then there's the crank that will actually propel this pulley system so that we can get these charges flowing. Now that we know the parts of the Van de Graaff generator, let's understand the physics.
When two insulators rub together, one loses electrons to the other and it becomes electrically charged. The belt and the pulley are both insulators. When the rubber belt moves due to the hand crank, charges are separated. Here at the bottom, the electrons from the belt will transfer to the plastic pulley due to the triboelectric effect and acquire a negative charge. The electrons on the outside of the belt are transferred to the pulley due to the repulsive force of like charges. The way they transfer is that they will travel through the air, through the electric field, to the brush located right here, connected to the ground, which allows for a path for those electrons to move freely and out of the Van de Graaff generator system. This results in the outside of the belt of the Van de Graaff generator having a positive charge. So now I'm going to take off the sphere once again so we can see what's happening on the inside. The charged outer surface of the belt attracts the electrons of the sphere through the metal comb. Recall that electrons move freely in a conductor, so the electrons move from the metal conducting sphere to the metal brush and are transferred to the outside of the positively charged belt due to that attractive force between different charges. When the belt moves down from the pulley, it is negatively charged due to this transfer, leaving the sphere to have a net positive charge. So once again, the result of the motion of the belt and the interaction of attractive and repulsive charges is a net positive charge on the dome. The positive charges spread out throughout the dome and become uniform due to the electrostatic repulsion. The net positive charge will continue to grow and increase the potential voltage and strengthen the electric field surrounding the dome. So, when a neutral object, such as this grounded wand, comes near to the sphere, the air will break down as an insulator. That plasma that you see is a state of matter where all of the electrons are able to move freely. The reason you're able to see that blue shock is because those electrons heat up the surrounding air and make it glow. So once again, that plasma zap occurs because the electrons transfer from a neutral wand and are attracted to the net positive charge of the dome. They are transferred through the air because of the strong electric field of the positively charged dome. Alright, so now that we've learned all of the different parts of a Van de Graaff generator and also the physics behind how it works, we're going to do one more fun demo. In my hand, I have some ordinary pie tins. Now these pie tins are conductors, just like the sphere of this Van de Graaff generator. So, when I place it on the Van de Graaff generator, once we get those charges moving, let's see what happens.
I hope you found this video helpful and now have a greater understanding of how a Van de Graaff generator works. If you have any further questions, please refer to your textbook or contact your professor.